Welcome to Data Skeptic Time Series.
This is Data Skeptic Time Series, the podcast about how to predict the future based on historical sequential data. Episode number... Matrix profiles are a mathematical tool that helps you find subsequences of time series and calculate the distances between them. This novel technique opens up new opportunities for time series analysis, and luckily you can try it out with the Python library Stumpy. Today I speak with Sean Law about the library, the method, and some use cases for matrix profiles.
Hi, I'm Sean Law, Principal Data Scientist, working at a Fortune 500 financial firm called Charles Schwab, and I work on their technology R&D team.
And what sort of data science does that entail? What's the skill set you bring to the table?
That's a great question. So I think usually for us, while there's a lot of obviously data science, machine learning, and artificial intelligence hype that's out there, I think usually from my perspective, right, is how do we find non-obvious problems and then try to solve them using non-obvious solutions, but that leverages data. That's sort of how I view my role on this research and development team.
And what are some of the tools or technologies that you typically rely on?
Usually from my perspective, because we're doing R&D type work, we try to leverage technologies, modern technologies that allow us to move quickly and to build proof of concepts at a rapid pace. And usually that ends up being leveraging tools in the PyData stack, so a lot of the NumPy, Pandas stack, also other tools that allow us to do not only parallel computing, but distributed computing as well.
For listeners who aren't yet familiar with it, what is Stumpy?
So Stumpy is a Python package that's based on some academic work that was published at the tail end of 2016 by researchers at the University of California, Riverside, as well as the University of New Mexico. Eamon Keogh and Abdullah Mouin, along with several grad students, published a series of back-to-back papers that describe this concept related time series analysis called matrix profiles. And essentially, matrix profiles is, imagine if you have, let's say a year's worth of data. So you have one data point every single day. So that's 365 data points. And imagine if you take a 7-day sliding window, maybe Monday through Sunday, and you slide it over by one day and you scan across your entire time series. Each of these windows is referred to in the literature as a subsequence. And the goal here is for every subsequence along this full year's worth of data, try to find the nearest neighbor for each subsequence. Right? And that's essentially what the matrix profile is. So it sounds simple, at first glance, but it turns out that as your data size gets larger and larger, computing this matrix profile or finding this one nearest neighbor for every subsequence becomes quite hard. Now, while it's very easy to interpret these results, and when I say comparing subsequences, it's typically computing some sort of z-normalized Euclidean distance. Right. But as you scale to about 10,000 data points or so, computing these nearest neighbors is very computationally expensive. And so that's what really where Stumpy comes into play, is that it reproduces that academic work and tries to faithfully produce the same results and the same performance as well.
Well, I definitely want to explore some of the algorithmic aspects of it. But before we get into that, can we talk a little bit about these neighboring subsequences? Could we maybe ground it in a real-world use case? Is it finding two, 4-day weekends that are similar in retail sales? Or what's the purpose of finding a neighbor?
Yeah, so I think there are maybe a couple of angles, right, in terms of practical use cases. The first thing is for exploratory data analysis. So a lot of the times, even for myself as a former scientist, I dealt with large amounts of time series data. And especially when you get this time series data into your hands, or maybe you generate it or you download it somewhere, even if you're a domain expert, trying to figure out where should I focus my attention on first can be a challenge. And so oftentimes when you have this time series data, the first question you might ask is, are there any patterns, even if they're roughly related patterns, in my time series data? And if there are patterns, where are they? And then the last question is that once you find out where they are within that time series data, you can ask yourself maybe an easier question, which is how many times does it repeat itself, right? And oftentimes when you're able to do this, then teasing out the next step, which is why is there repetition in patterns? That's usually the more interesting things. But the first three steps are, again, they sound quite simple, but they're actually quite hard to get towards.
As a user of this library, do I have to bring in some sort of parameter like my minimum or maximum sequence? What do I have to do to get it going?
So the really good thing about matrix profiles, especially as it's implemented into Stumpy, right, is that all you need to do is to bring your time series. In fact, to calculate these matrix profiles, you don't even technically need time. So time actually isn't being used in the calculation. And so you might refer to that as just simply a sequence. right, of ordered data points. And so that's essentially what you need. And then you need one other parameter, right, which is to define the window size. With those two things, then you can compute the matrix profile for your time series.
And when I have that matrix profile, what do I tangibly have? Is it a vector or some, pairs? What do I get as the output?
So you essentially get another series back, but you can use that series to annotate your original time series. And the way that this matrix profile works is that it is nearly as long as your original time series, minus some chunk at the end, which is equivalent to your original starting window size, right? Because you're applying a sliding window calculation. And as you move across this matrix profile, what you're really identifying are local minima or even global minima across this matrix profile. And wherever you have these global minima, those are really representing areas within your original time series where there's a potential pattern, or in the literature, they call these motifs, right? So motifs you can kind of think about as a potential pattern, and that's where you should look first, right? So every time you compute a matrix profile, plot it and look for the global minima. And then after that, you look for local minima, right? But each time you're looking at these minima, these are potential patterns, right? And then you can look at them, you can compare not only the subsequence located at that minima, we can also then compare it with the one nearest neighbor, right? Your top nearest neighbor, and see how close they are. Right? And you can sort of overlay them. And so that quickly orients you to say, oh, this pattern seems to be reasonably well matched. But it also, afterwards, you can ask the question, well, is this just a one-time match? Or does this pattern also repeat itself several times, right? So if you might have some seasonality or periodicity within your data, you're able to leverage this matrix profile and leverage the Stumpy to do a lot of this work for you.
Well, the usage of the word motif for me is evocative of music. I'm thinking of like a Bach concerto where there's a motif, a theme that plays out. Maybe we see some variation or the key changes. And I guess I could get that music in a MIDI format and represent that as a time series. Would Stumpy help me do musical analysis?
So in fact, one of the papers published by the original researchers actually demonstrated one of the classic examples, right, in sort of modern pop culture is the bass line coming from the hit song Ice Ice Baby by Vanilla Ice, and then compared with another song by David Bowie and Queen called Under Pressure. And like the first few bars of that song, it was argued, I guess, that part of the Vanilla Ice's song was taken from Under Pressure. And in fact, one of our tutorials in one of the original published work actually shows that if you analyze the frequencies, if you take the audio and you map it into what is called a MEL frequency, so into a frequency space, and you actually compare the baselines, you're able to see using Stumpy, you input these two time series, and it will actually show you where the two songs are very, very well matched. Right? And you can see that in one of our tutorials. I encourage everybody to take a look because it's a fascinating find.
Well, I'm curious about the robustness of the approach. The musical find's a really interesting one. What if we go in a totally, what to my mind seems radically different and looked at like climate data or seasonal weather information, things like that? Will the library hold up as well?
Yeah, I think the first thing to maybe point out and admit, right, is that obviously the use of matrix profiles should not be viewed necessarily as a silver bullet, as many other tools claim to be, right? But instead, it should be viewed as an opportunity to leverage a tool that can compute this matrix profile quickly, and that should be used as a complementary tool alongside all of these other ones, whether it's your more classical visualization capabilities or building ARIMA models or even using deep learning, right? All of these should be used in tandem. I think that the reason why Stumpy wasn't, or matrix profiles weren't popular prior to now was that it turns out that to compute the matrix profile, it would have taken a very, very long time, even on moderate data sizes. And what this new work allows us to do is to actually be able to scale up to larger data sets. So in terms of being able to robustly hold up, I think it's quite good. But I think what it also provides too, right, is the ability to easily interpret and analyze your results, right, without performing any mental gymnastics. I think that's one of those things where oftentimes with more classical methods of time series analysis, you kind of have to be an expert to know how to tune and interpret the results. Or maybe if you're building a machine learning model, how do you interpret the results and the predictions from there? Here, with Stumpy, with matrix profiles, the only thing that really requires interpretation or selection, right, is the window size. But with a little bit of domain expertise, that usually is sufficient. But there are also tools that Stumpy offers that allows you to maybe gloss over that point a little bit as well.
So when I'm thinking about how this is going to scale up, you'd mentioned some computational complexity challenges. What is the sort of original, before these papers, how would this scale in the size of the time series?
In the most naive approach, so let's say you have a time series of length n, so n data points, and you choose a subsequence size of size m. So the naive way of computing a matrix profile would require a computational complexity of n squared by m, right? And so the academic researchers had been working on this for some time, and you could maybe reduce some of that computational time down a little bit by applying some heuristics. What they then first realized was that they could use fast Fourier transforms, a pretty classic approach to analyzing time series. They could reduce that time from n squared by m to n squared log n. And then that was their first paper. But then they realized that with some very nice math, and there's no approximations here, this is exact, with some very nice math and some sort of nice discoveries in terms of how to traverse this sort of time series, they realized they could actually compute the full matrix profile in O of n squared time. So it doesn't even depend on the window size itself. And then they went on to publish yet another paper where not only do you compute it using your CPUs, but this is actually turns out to be a very parallel task. And so they ported this over to GPUs as well. So they could compute matrix profiles that are, by today's standards, very, very large, using GPUs within a few hours, if not a few days. And so to give you an approximate example, so in the original work, they showed that for a time series of about 100 million data points, n equals 100 million, they're able to use their GPU implementation and compute the matrix profile in just over 12 days. Now, 12 days might sound like a long time. However, if you think about collecting data points over a period of time, maybe like you have some IoT sensor that's collecting data every 3 seconds for 10 years, that's 100 million data points. So the amount of time that it takes you to actually analyze the data, even though it's 12 days, it takes you much, much longer time to actually collect that data, right? So you can argue that from an analysis standpoint, you can do this work in essentially real time because your analysis is faster than the time that it takes for you to collect your data.
Are these exact techniques, or is there something lossy about them?
There's actually nothing lossy at all. So these are precise, exact techniques. So unlike other, maybe let's say machine learning methods or other types of model building methods, right? Oftentimes you're going to lose some fidelity. But in this particular case, these are exact methods. When it says that it is computing a one nearest neighbor, you have a very exact confidence that the one nearest neighbor that it finds is the nearest one and nothing else should be closer.
Well, taking advantages of distributed computing in the GPU opens up a lot of elastic potential. Is this embarrassingly parallel, or is there some algorithmic challenge that puts limits on that?
Yeah, so one of the key insights from the published paper that I encourage folks who are interested to go and read, which is their Matrix Profile 2 paper. And so what they recognized was that instead of classically if you take a time series, right, and you're sliding a window across it, essentially you're comparing every subsequence within your time series with every other subsequence within the time series. And so that's where the n squared comes into play. But it turns out that they recognize that there's a certain way of traversing this sort of n squared matrix, distance matrix, so that you can reuse a lot of the computations. And that's where the benefit comes in, right? And maybe to simplify this, the way that they traverse this distance, the computation of the distance matrix is actually they traverse it diagonally versus across rows and columns of your time series. And so it's actually quite hard to implement accurately. And that's really where Stumpy comes into play, right? Is that we recognize that there's these algorithms and they perform very, very well. Now, the original authors published their work as well as releasing their code, but it was written in MATLAB and raw CUDA code. And so what we've done with Stumpy, right, is to offer up a very easy to install and use API, and that also matches the original work from the authors. And what we're trying to do here, right, is not to reinvent any wheels, and we're not trying to be the tool that solves all problems. But hopefully Stumpy, what it does, really highly focused on, is computing the matrix profile as fast as possible so that you don't have to do that work. And hopefully once you have that matrix profile, you can do a lot of other very fascinating or interesting things thereafter.
So if I want to use Stumpy, I may or may not have a GPU, depending on the age of my machine or what I paid for it, I guess. What do I have to do to get started? Is that a configuration setting, or does Stumpy figure it out for me?
Yeah, so Stumpy offers both CPU as well as GPU computing. And it actually, believe it or not, only has 3 core dependencies. So it's a Python package that requires NumPy, SciPy, right, which most data scientists will typically use, and then Numba, NUMBA, which allows you to write Python code that can then JIT compile that code into performant parallel CPU code. But you can also take that code and rewrite it to target CUDA as well. And so if you don't have a GPU, then you can just call Stumpy directly. One of the common functions that you'll call is something called stump, and that will just work on your local CPUs. Now, if you have a cluster of servers that you have access to, and you have a package called Dask installed on them, you can actually just pass into Stumpy the Dask scheduler and then it will handle everything else for you. Now, if you want to then take this work, right, and compute your matrix profiles using GPUs, all you need to do is just prepend 4 letters to the function. So instead of calling stump, you just call it GPU_stump. And the API or the interface is identical in both cases.
So I think you'd mentioned that it was able to run on up to 100 million time series entries. So obviously scalable and performant, even if it took a few days. I'm thinking now, though, about maybe the people in the longer parts of the tail. You've worked at a company, they have 3 years of data, maybe it's daily data, or let's just say hourly, 365 times 24 times a few years. That's not a whole lot of data points. Am I going to feel any scalability challenges, or is Stumpy going to seem rather instant?
Yeah, even for that data size, it's actually pretty good. I frequently perform matrix profile calculations on my laptop here. So usually for, I'd say, around 1 million data points or so to about 2 million, you can safely run it on any sort of modern hardware with any modern commodity hardware, I should say, right? But anywhere north of about 2 million data points, you'll probably want to start looking at either distributed computing or GPUs. And those are usually your options. But there are also alternatives too, right? So Stumpy offers something called an approximate matrix profile. So, or maybe just even taking a step back, you can also take your time series and downsample your time series, right? In order to identify which parts of your time series might have a potential pattern or a motif in it. And so that's the first thing that you might want to do. Even if you have 1 million data points, or if you have 100 million data points, you can downsample maybe to 1% of the original time series and then compute your matrix profile. But in addition to that, you can compute what I mentioned earlier called an approximate matrix profile, which as you're traversing these diagonals and computing these distances, maybe you don't compute all the diagonals, but you compute a subset of them. And you can incrementally compute more and more diagonals across your distance matrix until you eventually get back your full exact matrix profile. But usually the original researchers have demonstrated that you can compute even 1% of these diagonals or these distances, and you can get a pretty good idea of where the minima are located within your time series.
Thanks to our sponsor, HelloFresh. With HelloFresh, you get farm-fresh, pre-portioned ingredients and seasonal recipes delivered right to your doorstep. I love that it's pre-portioned because you can go to a restaurant and order something that has 9,000 calories in it. With HelloFresh, I know not only what I'm going to eat, but what it's made out of. Linda loves the farm fresh aspect because she's a little picky on ingredients, but HelloFresh always passes the test. Now, for Data Skeptic listeners, they sent me some real good stats. This comes from Zagat's Dining Survey. HelloFresh is 72% cheaper than a restaurant meal of the same quality. I can attest to that. And you can save on average over $65 per month when you order HelloFresh instead of grocery shopping. That's more money to put towards the other 2022 goals of yours. And Linda's a pescatarian, so not every meal kit's good for us, but at HelloFresh we've got a bunch of options. It is so great to not have to plan ahead. I get better meals than I would have dreamt up on my own, and they send me just what I need, not a bunch of extra stuff that's going to clog up my fridge until I throw it away 3 years from now. Listeners, if health and nutrition's part of your 2022 plan as it needs to be mine, I encourage you to go to HelloFresh.com/DataSkeptic16. Use that code DataSkeptic16 for up to 16 free meals and 3 free gifts. You cannot go wrong with that. Get America's #1 meal kit by visiting HelloFresh.com/DataSkeptic16. And 16 is 16. Thanks to our sponsor, mParticle. At the end of the day, your customer has to be at the center of everything you do. This starts with the right customer data strategy, as well as the right foundation to solve the challenges that typically inhibit success, such as data quality, data governance, and connectivity. mParticle is your real-time customer data infrastructure that helps you accelerate your data strategy by cleansing, visualizing, and integrating your customers' data from anywhere to anywhere. Ultimately, better data leads to better decisions, better customer experiences, and better outcomes. See why the best brands choose mParticle. Visit mParticle.com to learn how teams at Postmates, NBCUniversal, Spotify, and Airbnb all use mParticle's customer data infrastructure to accelerate their customer data strategies. That's mParticle. Better data, better decisions, better outcomes. Visit mParticle.com to learn more. Well, Well, the library's been out for a while and achieved a certain amount of success. Have you heard back from any users enough to get a sense of what some of the common use cases are?
Yeah, definitely. We've been pretty excited and humbled by the amount of interest, and we just surpassed our 1 million download mark. And so there's a lot of work that's still yet to be done, but we really are appreciative of all the support in the community. Some of the use cases that we've seen, one of the first ones actually came from researchers at the Large Hadron Collider, where they were looking at how to apply matrix profiles to learn or to identify potential patterns in, I think it was some sort of ion particles that they were trying to accelerate or pump through. And they're trying to understand if there were certain patterns that existed, all these toggles and switches that they can apply to their data. Another common approach that people will leverage Stumpy for is to look at trading data. So obviously, like things like daily closing prices, is to maybe try to make more informed decisions, trading decisions or investment decisions using Stumpy. Alternatively, one very sort of creative approach came from some folks that were trying to leverage Stumpy to analyze call transcriptions. Not necessarily the words themselves, but let's say you have an employee at a call center and a customer that's calling in. And what they did was that every time the employee spoke, they would add +1, right? Every time the employee spoke a word. But every time the customer spoke a word, it would be -1, right? So you kind of have a time series moving across, right? So if the employee spoke a lot, then the time series would go up a lot, right? And then if the customer spoke, then the time series would go down. And what they were trying to do was to identify across multiple conversations, right, with different customers, are there sort of commonalities, right? Maybe a certain subset of employees spoke a lot up front, right, versus letting the customers talk. And so that's how they were able to identify almost like a story arc in a book, but just by analyzing these transcripts.
So you'd mentioned the Stumpy library being largely inspired by the series of papers. So I guess in some sense that's the origin, but when was the first line of code written, and what was the impetus to start a project like this?
Interestingly enough, the original authors published their paper in the fall of 2016, and I actually came across it in just a subreddit where the original authors posted it. And when I read it, I was quite surprised, especially the claims in the abstract of being able to find these patterns. And having analyzed time series data for almost a decade prior to that point in time, I felt like it was too good to be true. And so in around the beginning of 2017, I found some time, being on an R&D team, I found some time to actually look at this research. And then I wrote my first piece of code probably somewhere by the end of January 2017. I wrote it in pure NumPy, and for about 10,000 data points, it actually performed very well, and I was quite impressed and surprised. Once I started increasing the number of data points, let's say to 50,000 to 100,000 data points, it started to slow down. Now, obviously, these are part of the limitations of NumPy, because even if you have vectorized code, oftentimes it can fall back to using a single core on your machine. And that's when I ported it over into Numba, right, which then allowed us to parallelize this computation across all the cores on a given machine or server. And then I also leveraging Dask, was able to distribute this over 32 servers, right, 256 CPUs. So if you look at our performance metrics, which is in our README, you can kind of see that this actually scales very well. But from 2017 was when we actually internally wrote this code.
Well, you've touched on this a little bit in that answer, but I'm still going to ask anyways. Are there any lessons learned or challenges in translating academic work into actual tangible code?
Maybe I'm a little bit lucky being a former academic. I've also written a lot of academic code previously, but I've also been forced to read a lot of academic code, whether it was in Fortran, Perl, or other languages. And I will say that because the original authors wrote their code in MATLAB, and I understand that when you're in academia, your goal isn't necessarily to write the most elegant or beautiful or performant code necessarily, right? Your goal is to publish papers. And so without being overly critical, when I first tried to implement the first version of their algorithms, I actually got stuck. And for maybe a couple of weeks, I was sort of banging my head against the wall, like wondering, why is this wrong? Because given that their computing matrix profiles you can do this naively, I could compare my results to a naive implementation, and the results weren't coming out correct. And so finally, I reached out to the original authors and I asked them the question of like, hey, here's my code and I'm finding this error. And it turns out that one piece of the code where they had published it, there was an off by one error. And so in my code, I didn't have that error, right? And so luckily, I was able to also submit a pull request to their work to kind of fix that. But it was a good learning lesson, right? That oftentimes there are errors, but hopefully we can get through this. But again, I think that this really emphasizes the point of Stumpy is that doing these things or porting code over from academia into industry can be challenging. And hopefully with code or packages like Stumpy, right, you don't have to go down that path and be confident that what we're providing for you is not only correct, but also scalable available too, right? I think for Stumpy, since day one, we ensured that we have a full unit test suite, but as well as 100% code coverage. Even 2.5 years later after first open sourcing it, we still maintain excellent code coverage.
What was the motivation to open source the project?
So I think there are a couple of things. The first thing is, as a finance firm, we obviously consume a good deal of open source. And I think for many of us, especially the developers at our firm, we wanted to find ways to be able to give back. And with Stumpy, I think it was our sort of first venture into contributing to open source. So not only consuming open source, right? And I think that this has been a great way for us to give back to the community.
So I know Stumpy's being used in a lot of different places and different contexts. So it's a working, stable system, but I also see from the GitHub it's active and there's contributions going on. What's being worked on?
I think right now, one of the most important things is adding stability, continued stability to our code base. But one of the most exciting contributions comes from a group of students, both from the Columbia University as well as the University of Waterloo in Canada, where they're helping improve the performance of Stumpy. Initial results are demonstrating that we're able to improve the cache misses, the memory cache misses, and reduce the computation time, at least on the CPUs, by about 20% just out of the box. We're going to perform some further tuning on this, but we're optimistic that we'll be able to squeeze further performance. So things that might take you, let's say, an hour to compute something, maybe rather large, right? You can shave off 20% of that time, which could be huge.
Well, I know there's a number of tutorials to help people get started, get exposed to the library, learn it through some examples. Could you share a few details on what the onboarding path is for a listener who's curious to get started with the library?
Yeah, there's probably two main ways for people to get started, right? One is to go through our tutorials. We do have a video as well in our background and motivation tab in our documentation, which basically gives you a quick run through of the basic foundation of a matrix profile. But our tutorials actually all reproduce the published work or examples and figures from the original published work. So to give you a sense of confidence, right? That when we say that Stumpy works, that it is grounded in real live examples. But also what we do in addition to the original published work is that we take the concept and the explanations and we try to lay it out in more words than is available in the original work. And so hopefully you'll be able to learn not only the API, but also how to think about matrix profiles and all of its applications. One other place that is great for people to get involved is in our discussions. So if you ever have any questions about matrix profiles or about Stumpy usage, we encourage you to go to our GitHub page and under the discussions tab, get involved in our community. We already have, in addition to myself, many members of the community who are actively engaged in helping to answer questions, regardless of whether it is directly about the usage of Stumpy or even about the nuances of how you might need to prepare your data or manipulate your data in order to get it into the right shape to be used in Stumpy.
Well, as you know, we're several months into our season on time series here at Data Skeptic, and I guess I'm sad to say I think this is the first time we've discussed matrix profiling on the show. Perhaps that's because it's been relatively recent that it was more practical to use, these series of papers in the library and things like that. Where do you see it in 5 years in the pantheon of tools that people working on time series look at? Will it be right next door to ARIMA in terms of prominence, or is this for special cases?
I think that in my mind, and then probably in the original researchers' minds too, right, is that this is something that is now practical to do, right? Being able to compute these matrix profiles. And prior to 2016, you could apply it to toy data sets. And so realistically, you want to, in my opinion, whenever you have any new time series, I usually remind people that instead of debating or arguing which method you should choose, right? You should choose the set of tools that allow you to move quickly and to gain insight into your data as quick as possible. And a tool like Stumpy sort of serves that purpose, especially in the realm of exploratory data analysis, because once you analyze it and obtain your matrix profile, you immediately get a sense of where you should start focusing your attention on first. And oftentimes that generates new hypotheses of where else you should explore in your time series. And I do think that in the next 5 years, as we see more and more people publishing papers, up to this date, I think there's about 350 publications that cite the original published work, right? And that number continues to grow. And so I certainly hope that matrix profile becomes more and more mainstream, but should end up being a typical tool that you reach for almost instantaneously whenever you're analyzing any time series data. And in addition to that, I would say that, again, that matrix profile, it's not an or situation where you have to choose one tool over another. In fact, matrix profile should be a complementary tool to many of the other time series analysis as well as modeling tools. I've already seen some papers being published leveraging matrix profiles as generating features for machine learning models.
Could you talk more about that? What sorts of features do people develop and how do the models consume them?
Yeah, so I think from my perspective, one thing that's quite valuable is for every subsequence within your time series, not only do you get to know that there is a one nearest neighbor, but you get the distance to that nearest neighbor in the Euclidean distance. But also what's interesting is that you get to know the position of that nearest neighbor along your time series. Maybe you have a nearest neighbor that is 100 days or 365 days into the future. But for every subsequence, you get to learn this information. But you can also have a nearest neighbor that's in the past too, in history. And so this type of knowledge can certainly be used in machine learning, right? To find out if there is a nearest neighbor or a pattern, where is it? Like how far away in not only Euclidean distance, but positional distance along the time series. But is it in the future or in the past, right? So when it's in the past, we kind of, in the literature, refer to that as a left nearest neighbor, versus if it's something that happens in the future, it's also a right nearest neighbor. So that's definitely some ways that you can incorporate some of this knowledge and insight into your machine learning models, right? So maybe in one of your machine learning features might be, what is the distance to a nearest neighbor? But also maybe a different column is positionally, where is that nearest neighbor located? Is that nearest neighbor located 20 steps ahead or 20 days ahead? Or is it 365 days prior to the current subsequence?
Well, in the pre-interview, we talked a little bit about this project I'm working on at Data Skeptic, doing an episode about Black Friday. Is there anything novel or insightful that matrix profiles can help teach me about this retail event?
Yeah, absolutely. So in one of the original research papers, there's a topic called time series chains. And really what this means is that if you take your time series and you compute the matrix profiles, the question that you can ask is, for a subsequence, where's that nearest neighbor located? And so if it happens to be located in the future, then for that subsequence, where's that next nearest neighbor located? And so you can kind of have this chaining effect, right? Where you keep moving forward in time, across time. And they demonstrated in and once you compute these time series chains, their example that they used was looking at Kohl's retail stores. So how many people were performing a Google search for the word Kohl's? And they actually showed that there's some, not only seasonality across time, right? Presumably if you have a growing business. But they also noticed that when you compute the matrix profile, it identifies global minima near the end of the year. And so the first minima, there's two of them. The first one happens on Thanksgiving. And then there's a second minima that happens in around Christmas time period. But what they then notice is that thanks to these time series chains, that year over year over year, that first hump increases and overtakes the second hump. And the reason being is that in around, I guess, 2007 or so, there was the creation, I guess, or reimagination of a day called Cyber Monday, where people are increasing their Google searches. And so leveraging matrix profiles, you're able to see this. But as proposed in the paper itself, they were even suggesting that because you've identified these patterns over time, you might then be able to take this information and think about potentially forecasting what next year's search query amount will be.
On a lot of time series data that we've talked about this year, it's, real world data, which is good. And the real world has been through this very novel event in the pandemic that shows up in a lot of time series. Do you have any broad thoughts on how the impact in certain areas and problems that Stumpy might be applied to would impact the way the matrix profiles get formed?
Yeah, so I think the best way to address that question is actually from one of the original papers that was published, where they looked at earthquakes and being able to identify within a given region that there are certain patterns that can potentially be extracted from earthquake data. But oftentimes earthquakes can happen over several decades. And similarly speaking, right, we can look at being in the middle of a pandemic. How does the data that's generated, the time series data that's generated over the past 18 months to 2 years, how does that look? And how does that relate back to previous pandemics in our history? And so I can imagine that if there are any patterns, one should be able to extract that. And given that the data size is hopefully not exceptionally large, you can do that pretty quickly using matrix profiles and using Stumpy.
Before I go into any sort of wind down, I like to ask, is there anything you think I should have asked you that we didn't get around to?
Yes, streaming data. I think that's probably one topic that comes up rather frequently, mostly related to finding anomalies. So I think one thing that I mentioned about matrix profiles is that if you look at the minima within your matrix profiles, right, that tells you where the motifs or the potential patterns are. But there's actually an alternative use of the matrix profile, which is looking at the global maxima. And those global maxima basically tell you that for a given subsequence, there's not a particularly good match, in which case those are called discords or potential anomalies. Now, taking this a step further, a lot of times folks who are maybe in industrial settings or IoT settings where you have machinery or devices that are collecting data. And really what you want to be doing is to be able to compute matrix profiles along some window, maybe a month of data, right? And you want that month of data to be updating across time. So Stumpy actually, again, based on the original published work, offers incrementally updating matrix profile that performs quite well on streaming data. And it's exceptionally lightweight and works very well.
Could we expand on that a little bit? Imagine maybe I've got a Kinesis stream or a Kafka implementation, and these events are flowing through my system. Do I make updates on every event, or do I batch them? In practice, how do I use it?
So the thing with a matrix profile is that when a new data point comes in, nothing actually fundamentally changes, except for the fact that new data point produces a new subsequence at the very, very end of that time series. And so all you have to do is take that new subsequence and ask the question, where's the nearest neighbor to this newest subsequence? And so you don't actually have to recompute any of the distances prior to that. So those, you might compute them once at the beginning, right? But as a new data point comes in, you just only have to update the nearest neighbor for that one new subsequence, as well as, where is the location of its nearest neighbors. And also, in addition to that, there's this question that people might not realize is that when you're dealing with streaming data, oftentimes because you don't have the full data set, what you really want to be doing is asking, where's the left nearest neighbor? Right? So you should only be looking in history, because you can't cheat and look into the future because you don't have that future data yet. And so out of the box, you can do this very, very easily with Stumpy. So you provide your original time series, maybe whatever data you have so far, and then you tell it what window size do I want to compute matrix profiles on. And as each new data point comes in, you literally just call an update function, provided that new data point, and it will update the matrix profile on the fly. And you can see that in one of our tutorials as well, that is called the Incremental Matrix Profiles for Streaming Time Series Data. And there's an example at the very, very bottom where you can see as new data points comes in, how does that matrix profile update itself?
Do I pay any computational cost doing it in this streaming real-time setting?
No, maybe with a little bit of a caveat. So as new data is streaming in, as long as you egress is what they call it, right? You remove the oldest data point, then you don't really pay much of a cost at all. It's essentially fairly straightforward. The only problem is that if you don't egress that oldest data point, at the very, very left of your time series, as new data point comes in, that time series will grow bigger and bigger and bigger and bigger. And so updating the length of your matrix profile requires copying memory around. So that's usually not recommended, although it will still do that, but you probably have to add a lot of data points before it really starts to matter. But it also depends on the frequency in which those data points are coming in too, right? If you're receiving a data point every second, every minute, it probably doesn't matter so much, even out to 100 million data points.
And are there any sectors or industries that you think have underutilized these techniques where you'd like to see some elbow grease and effort put in the coming months?
I think that, as we just mentioned before, I think IoT is a very fascinating space where there's a large amounts of data that's coming in frequently, but also, again, the usability for academia, right? I think that as a former academic myself, I really wish that there was some tool that allowed me to, focus my attention on certain parts of the time series, right? And I think that this, just like Excel or NumPy is to the academic world, I would love for Stumpy to serve that same purpose for any type of time series data that they may have. And then obviously from a finance standpoint, people who are analyzing large amounts of quantitative data, I would love to see more people leveraging Stumpy as well.
And remind listeners, where's the best place to get started?
Yeah, so to find Stumpy, just go to stumpy.readthedocs.io and you'll find all of our tutorials and all of the background information there. For the code itself, you can go to GitHub.
Very cool. We'll have links to both in the show notes. Sean, is there anywhere people can follow you online?
Yeah, I'm pretty active on Twitter. You can find me at SeanMyLaw. And then for Stumpy, you can follow the development and release announcements on Twitter as well at Stumpy_dev.
Well, Sean, thank you so much for taking the time to come on Data Skeptic.
Thank you for having me. It was a pleasure.
That concludes another installment of Data Skeptic Time Series. Our guest today, Sean Law. Thanks to our sponsors, HelloFresh and mParticle. Myself, Claudia Armbruster, as associate producer, Vanessa Bly, guest coordinator, and our host, Kyle Polich.